Assalamu alaikum. How are you?
Assalamualaikum, sir.
Salam. Did you start the homework? Yes or
Sir.
no? Or you will
Yes,
start
sir.
on a weekend? Okay, good. If you start late, it will be actually on a hurry. Okay, I did not update yet on the homework page, but as I said, I will extend for 1 week, 1 day, but after that, it will not be extended. Okay, and we have one more chapter left for our final exam syllabus. I think today is our 21st lecture, right? So we have 3 more lectures, and hopefully we will get at least half of the last class to discuss about the final exam and other questions, confusions about the syllabus. And also we have our last class test on coming Saturday, right? In our next class. And the syllabus will be chapter 4 and 5. So 4.1, 4.3, and then 2 algorithms in section 5.2. Okay, and we have covered linked state algorithm, and in the last class this distance vector algorithm. So before we go to today's lecture, anybody has any question on the previous class? If you just
Sir,
yes,
yes, I am facing some difficulties in solving the assignments set of force.
which one?
Solving the assignments questions from chapter 4 and 5, sir.
Chapter 4 and 5, question from the assignment.
Yes, sir.
Okay, tell me what is the problem.
Sir, can you please go to the question, sir?
Okay, okay, this is the question.
So from chapter 4, sir, 4 and 5.
Question what? Chapter 5.
Yes, sir.
Which question? Question number?
Here the question number is, sir,
Is
2
the
and
question number 2? Okay, question number 2, this one.
2C, sir. How to do it, sir?
Actually, I will not say how to do it because we have covered entire network address translation mechanism. So it's your responsibility to understand the scenario and then answer. Because if I tell you how to do that, then actually without saying answer I cannot do. Okay, because see, assume there is a scenario given. So in the scenario, you can draw the scenario, whenever NAT is used, there must be a public IP, and under the NAT, there are private IP. So all the information is given here. So you can draw. It's not mandatory, but you can draw and then you can understand. Then for every question 1 and 2, the scenario is given. IP packet carrying an HTTP request. We know HTTP is an application layer protocol. So application layer data incorporated into transport layer segment, right? Then transport layer incorporated into an IP packet. So this should be understandable to you, and understanding the scenario and then answering is part of the assignment. Then suppose both Sohan and Alim checking email. Checking email means using some network connection, searching some materials in Google, some network connection. So just you have to match this scenario with the example we have covered on net. Then it will be very simple. Okay.
Okay,
Is
sir.
it little bit clear now, Pratik? Because if I just show you how to do that, then it's almost the solution. I want you to think, I want you to connect with the example we have done in the class. But the example we have done in the class covers everything. There is nothing in this question that is not covered in the example in the class. Just let me tell you that's for sure. Okay. Any other question?
No, sir.
Okay.
In question 3A, what is the source?
See, going from
Sir,
going
question
from means
3,
what?
sir. Question 3A.
Oh, question 3A. Oh, what is the source? In Dijkstra's algorithm or linked state algorithm, which one is the source? For which we need to compute the forwarding table. So if I say the source node is F, it is same as if I say compute the forwarding node for F, because if you need to calculate the forwarding table for F, definitely F is the source, right? Clear? So even if I don't say F is the source, actually F is the source in this equation, because for the source you calculate the forwarding table in linkage. In distance vector, that is not the case. In distance vector, every node actually updates its own distance vector table at every step. So it show the calculation only for node B in the second step. So it's not like B is the source. Every node will calculate its own. You have to only show B's calculation up to second step. So first step, all distance vector will be there. In the second step, you have to show calculation and how B updates its distance vector. For question A, F is the source. So you have to calculate the forwarding table for F. Clear? Any other question? Any other question in the last class or the previous class, linked state distance vector? I think if you practice, then it will be fine.
Sir, in the final question of assignment.
Yes. Final question.
Yes.
Yes.
Sir. We have to just find t equal to 0 and t equal to 1, right?
Which one? Which one? 3A
B.
or 3B?
3B.
3B. Okay. Yes. You have to find. Okay. You have to find the distance vector for B in the second step. That means B will get updates from the neighbors, right?
Yes, sir.
From the first step. Then B will apply that Bellman-Ford equation, right? For each of the possible destination. I have shown it in the class, right? So for
Yes,
B, you have to show that calculation and the final table that B creates after second step. So second step, if you show up to second step, that's fine. You don't need to show the third step, fourth step. Clear, Mohib?
Yes, sir.
Okay. Okay, anybody has any other question?
ফার্স্ট স্টেপের জন্য কি সবগুলোর জন্য দেখাতে হবে?
For 3B?
Yes, sir.
Is only for node B. Only for node B. See? Show all the calculations to find updated table for node B after the second step. So you have to show only for node B, not other tables, only for a single node, that is node B. Okay, Shajol, clear?
Okay, sir.
Okay, so all the questions here, there is no question you can show me that is not covered in the class. Just you have to understand. Again, those who did not go through the basic example from the textbook, again you will find difficulty. Always I say, before doing a solution, confirm that you understand the basic example we have covered in the class from the textbook. There are lots of details specified there. When you are confirmed that, okay, I understand the basic example, then go for the solution. And there is a gap. If you just understand a concept using a solution, that will not help you very much. Okay. Anyway, I will upload after the deadline. I will upload the solution of homework 2 also after the deadline, so that you can match the problems or the mistakes you have done in the homework. And today we will basically cover one interesting part we did not cover in chapter 4 before. I think this will be also interesting to know for you, although IPv6 is a vast concept now. For the implementation, there are lots of details. We have not that much of time, but at least we can get some basic idea about IPv6, which are going to be implemented in near future. It's already there, but still IPv4 has most of the part of the network, because there are lots of problems to completely go to IPv6 yet, but IPv6 is there already. So you have to, I think it's better to give you some introduction on IPv6, so that later on you can use the concept anywhere you need. And then we will start chapter 6 today. That is the last chapter. And again, we will not cover everything in chapter 6. We will cover some selected sections as in chapter 4 and 5. Okay, so that is the outline. And those who join late, we have our final class test on Saturday, 25th September, and the syllabus will be chapter 4 and 5. Okay. Okay, so let us then cover IPv6 before we move to our last chapter, that is chapter 6. Okay, so okay, first of all, anybody know when actually IPv6 was started? Just started, because we think, okay, it may be 2 years, 5 years back, 10 years back. Actually, it's more than 20 years back. They have predicted that IPv4 is soon going to be depleted or exhausted, the IPv4 addresses. So they started a project on IPv6. I think it's before 2000 or near about 2000. But IPv6, I think, officially launched during 2006 or 7, and still it's a very low percentage of IPv6 in practice because of many reasons. First of all, why we need IPv6? Because of limitations of IPv4. So what are the limitations of IPv4? There are 3 major limitations. Sorry. The first one is IPv4 address depletion. So address depletion is the main cause. We have basically run out of IPv4 addressing. Then lack of end-to-end connectivity. You know, we have studied NAT, and NAT is very much in place everywhere in IPv4. What was one of the problems with NAT? I think we have discussed in the class. It breaks the end-to-end concept. When we say from source to destination, we said IP address will never change, right? In chapter 1, we have mentioned IP address will not change, but MAC address will change. But that actually is violated during NAT, because NAT changes the IP address in the middle. So it is lack of end-to-end connectivity. And those solutions, private IP address, NAT, were created ad hoc because it was created to solve some problems. That is another problem. Then increased network complexity. Although NAT has been invented to as a solution for IPv4 for temporary solution, but it created lots of problems in the network as a side effect of manipulating the network headers addressing. I think you can recall one other disadvantage of NAT we have discussed. NAT is implemented in network layer, right? But NAT uses port number. The router implementing NAT uses port number. Port number is implemented in which layer? Can you tell me? Port number is the field in the header of which layer?
Network.
No, no, no. Port number. Source port number, destination port number. Those are the head fields in, yes, Shajal, in which layer?
Transport layer.
Transport layer, right? Transport layer. NAT is implemented in network layer. So network layer should not access the transport layer header, but NATed router uses that port number for sharing the public IP address, right? So that is another violation of, not only violation, that creates the complexity. NAT causes latency, NAT causes troubleshooting issues, NAT causes complexity of application development, because now if NAT is in the place, an application cannot detect the end system directly using IP address, right? So these are the problems in IP version 4. And then IP version 4 actually introduced, started to develop that version 6. The initial motivation was like the address space. Definitely the address space. The 32-bit IP version 4 address would be completely allocated. And there is actually no more, as I said, no more IP version class A address available now. Some class C, some class B still available, but there is no more allocation as a new. Also, when they started to develop IP version 6, they have also identified some of the other limitations of IP version 4, like extra processing, delay. So those actually were also introduced in IP version 6 to improve, to make the processing more efficient, to speed up processing or forwarding. One of the thing is fixed header length. In IP version 6, the header length is fixed. In IP version 4, we had an optional field, right? In TCP, we had an optional field. In IP, we had an optional field. So whenever you have an optional field, that is variable. So you have to do extra processing for that. But whenever you have a fixed length header, less processing. So that is one other motivation for IP version 6. And also it enables different network layer treatment of flows. Data can be of different flows. Data can be, for example, of video data, or as application data with different applications, different class, different priority can be there. So flow is a concept that was introduced in network layer, especially in IP version 6, so that data in the network layer, packets in the network layer can be differentiated. Okay. And in this diagram, I think you can see IP version 4 exhaustion of the addresses in different parts of the world. For example, you can see the most advanced area is North America, right? America, USA. See, they have also in Europe. In Europe, IP version 4 exhaustion date April 2011, already 10 years back. The addresses or the blocks assigned was exhausted. That means no more blocks. In I think Africa, see, 2020. That means there's still lots of IPs there because they have not developed that much. In Australia, June 2020, 2014. This is the expected exhaustion date. In North America, I think it's in which one? Okay, Europe is 2012. I think in South America it's so you can see from 2011 to 2012, 2014, 2015. Only Africa has 2020 because less amount of space used. Anyway, so IP version 4 is exhausted or to be exhausted very soon or already exhausted. So IP version 6 was introduced with 128-bit addresses page. The development of IP version 6 also included fixes for IP version 4 limitations and other enhancements, as we have already said. With an increasing internet population, a limited IP version 4 address space issues with NAT, and also another important factor you know is IoT, Internet of Things. Huge number of devices will be in the internet or already in the internet. The time has come to begin the transition to IP version 6. So this is the main motivation and need for IP version 6. IP version 6 datagram format. You can see these are much simpler. Some are similar to IP version 4, but some are already obsolete or not already removed. So you can see the addresses are now 128-bit. So huge, 2 to the power 32 to now 2 to the power 128. And then there is a flow level, as we said, it's introduced to identify the flow of data in the network layer datagrams, network layer packets. And then priority, another important thing, identify priority among the different flows. So to identify different flow, another field can be used, that is priority. Version number is IP version 6. And what's removed from the IP version 4? If you compare, we have already also seen IP version 4 header format. No checksum. Now you can say, okay, why error? If there is an error, then what will happen? Okay, there are improvement in the technology. Also, data link layer has error detection facility. Transport layer has error detection facility. And as we said, what is the specialty of network layer? Okay, let me ask you, what is the specialty of network layer compared to other layers? Anyone? In short, in very short. What is the specialty of network layer in terms of, okay, let me give you hints, in terms of efficiency, in terms of processing compared to other layers? Whatever mechanism you implement in network layer must be done by every router in the middle, right? If a packet travels 20 routers, 20 times the processing must be done. You got my point? So that means if you remove one processing, you can make it 20 times faster. If you need 100 routers in the middle, you can make it 100 times faster. So that's why, since transport and data link, both upper layer, lower layer, has the checksum or error detection facility, in IP version 6, there is no checksum to speed the processing at the routers. Because of what? Because in the network layer, it is multiplied, okay, by number of routers. Then no fragmentation reassembly. Again, processing. You fragment, you have to process. Reassemble, you have to process. Make it more faster by removing fragmentation reassembly. So see, there is no field, that ID, flag, offset, no field here. No optional header. Okay, so although there is no optional header, we can also increase the header size of IP version 6. There is a provision kept here, that is the next header field. You can see the next header field here. Okay, here is the next header field. So next header field can also be used to extend the header if needed. But normally the next header field is the next layer protocol. For example, TCP, UDP. Okay, and then payload is the actual application layer data. Is it clear?
Sir, if
Yes.
there is no fragmentation, then how can we send a larger packet into a smaller bandwidth?
Yes, that's a good question. Actually, in that case, if a particular router sees, okay, the data link layer is not supporting the packet size, right? In that case, it will simply discard. Now, in the first sense, it might be seen as inefficient, but it's efficient in the sense there is a mechanism in IP version 6 so that so basically that fragmentation reassembly is removed means now the entire responsibility is to the end system, like transport layer. You can remember transport layer is implemented in the end system, so there is no burden on the routers. Similar things here. Now the end system must decide the packet size. Okay, there is a mechanism in IP version 6 also to know what is the lowest MTU in the path. If an end system knows what is the lowest MTU in the path, then the end system can create packets using that size. You got my point, Muhib? But
Yes,
we are not going to that mechanism, but there is a mechanism. But removing this actually make it faster, because you in Internet of Things, huge number of devices will be there. We don't know how many times we need to do the network processing. So the one of the primary idea was to speed up the process, and second idea was to make it more secured, to make it to remove the problems that those were in IP version 4. These was the motivations, and based on that they have actually proposed this IP version 6 header. There are some definitions. I think you can go through this. I have already specified this. Another important thing, if we know, that's better. How IP version 6 address will be represented. You have done in network lab IP version 4 addressing, subnetting, right? You have done. So if you do it for class A, it is a lots of calculation, right? In the subnetting part. If you do it class C, simple. If you do it class B, little bit more. If you do it for class A, the number of bits increased, your calculation will be like more time consuming. Is it correct? Because you have done IP address subnetting IP version 4. So if you need to do that subnetting using 128-bit address, will it be easy? Will it be very simple? For 32 to 128. Fortunately, you don't need that type of IP addressing subnetting calculation in IP version 6 because of some reasons, but because of lack of time, we are not going through that. In our professional CCNA course, Cisco networking course, we actually cover all these things in the networking. So those who are interested in networking, you can, if you want to know more, you can do that. But what I am trying here, I am trying to give you some concept at least in the computer networking class, so that you have the starting view, starting basic concepts. Okay, now how we can represent the IP version 4 addresses? You can see in the bottom there are two examples, 128-bit. So each IP version 6 address is converted to hexadecimal. You can see hexadecimal. You know hexadecimal. So 4 bits for one hexadecimal digit, and you can see the each part is divided by colon, right? So each part, how many bits? Can anyone tell me? Each part represents how many bits?
16.
Right, 16, because each one is a hexadecimal digit, so it's 4 bits. So 4 into 4, 16. It says it's a segment of 16 bits, and each segment is represented as a separate. It's also called nibble. It's also called nibble. So there are 1, 2, 3, 4, 5, 6, 7, 8. So 7 into 16, you can find it 128. So 128 bits represented in hexadecimal using colon in this format. Still it's large. If you want to write an IP version 6 address, it still is large. So to make it simple and smaller, they have used very simple 2 rules. First rule is omit leading 0. You cannot omit trailing 0, cannot. You can only omit leading 0. For example, if you see the example in the bottom, 2001, actually not 2000, it is 2001, 0db8, 000. So from each part, what you can do, you can remove the leading zeros in front. It will be no problem. So I removed the first 0 from db8, then db8. Then if there are 4 zeros, you can remove 3 zeros, keep 1 0. Similarly like this. Clear? Very simple rule. Remove or omit leading zeros, but you cannot omit all zeros. If there are 4 0, you have to write at least the last one. Is it clear? Okay. Still is large, right? Still a little bit of large. So the second rule says you can use more shorthand, what is called double colon. You can use double colon to replace a number of consecutive zeros, but once. So in this example, again, if you need to replace using a double colon, you can do it for third part, right? Or you can do it for fifth part. There are 3 consecutive 0 nibbles, 3 consecutive 0 nibbles, 0 parts. So if you do it the first one, you cannot do it for the second one. So you will logically will take the longer one, and then we'll replace this with double colon, and the first one will be replaced, but just applied the first rule, 0. Is it clear? Any question?
Yes.
So if you apply 2 rules, then it will be somehow, it will be in a shorter format. You cannot do more than that. But just remember, double colon you can use only once in the representation, because if you use twice, actually what the presentation do, it actually calculates the number of zeros in this double colon. How? Because it can easily calculate what are the number of bits in the other part. 16 plus 16, this 0, third 0 is also 16, fourth 1 1 1 1 also 16. So 4 into 16, that means 64, and the last part is again 16, so 80. So if you divide, if you subtract 80 from 128, you will get how many zeros are inside the double colon, right? So the logic is simple. So that's why you cannot use this double colon more than one time. You can use once. So logically you can use it for the longer phase of zeros. Also, if there is a 1 in the middle, if there is any non-zero in the middle, you cannot use double colon with it. You can only use double colon if there are all zeros in that part. So this is how we can represent IPv6 address in a shorter format using 2 rules. Third and final point about IPv6 is, as I said, it's very tough to implement, to use IPv6, to I think use or implement IPv6 in such a way from tomorrow everybody will use IPv6. It's not that easy, because there are so many number of ISPs, different type of devices in the internet using IPv4, and also a number of customers, they are using IPv4. So you cannot remove that IPv4 overnight. But we need to implement IPv6 at least phase by phase. So there are some mechanisms developed so that they can coexist. That means IPv4 also work, IPv6 also work. One of the mechanisms is dual stack. Those routers that wants IPv4 and IPv6 both to be used simultaneously, called dual stack router. So basically in IPv6 coexistence, you need dual stack routers. If you have a router only IPv4 or router only capable of IPv6, you have to use that router in either IPv6 or IPv4. But the intermediates, there will be some routers that needs to communicate between IPv4 to IPv6 and IPv6 to IPv4. They must be of dual stack. Okay. And then if you have dual stack router, then you can do 2 things. One is the tunneling. Tunneling means both sides is IPv6, but in the middle IPv4. Okay. For example, we are using internet using ISPs. ISPs use IP version 4, but probably my machine uses IP version 6. Then what will happen? Then there must be at least a dual stack router in my border, both sides. In that case, IP version 6 to IP version 4, there will be one translation, not translation, there will be tunnel between IP version 4 and both sides there will be IP version 6. So when a packet of IP version 6 is transferred to another end system of IP version 6, it will be in the dual stack router, it will be converted to IP version 4, and then it will carry on through the intermediate nodes, all are IP version 4, no problem. And when it reaches to the IP version 6 network, again there is a dual stack router that will convert the IP version 4 packet to the IP version 6 packet. That is the idea of tunneling. There is a tunnel in between. Translation is direct. If I want to communicate with IP version 6 to IP version 4 machine, or IP version 4 machine to IP version 6 machine, again it is also called NAT, but it's a different NAT. It's not changing the IP address, it's changing the version. IP version 4 packet can carry IP version 6 data, IP version 6 data can carry IP version 4 packet. So that is called translation. So these are the three mechanisms we need to actually use both IP version 4 and IP version 6 so that they can coexist. Okay, we will see one example on tunneling in this from this textbook. So transition from IP version 4 to IP version 6, as I said, not all routers can be upgraded simultaneously. No flag days. Flag days means, okay, it will be available exactly from 2023. No, you don't know how much time we still need to completely move to IP version 6. It depends on many factors. How will the network operate with mixed IP version 4 and IP version 6? I think we have seen that. One is tunneling. We will see an example on tunneling. So as I said, it's IP version 6 datagram carried as payload in an IP version 4 datagram among IP version 4 routers, because it's a packet within a packet, because in the intermediate network there are all IP version 4. This is one common place now. And tunneling is used extensively in other contexts also. For example, 4th generation, 5th generation mobile cellular network, but that is a different tunneling. But in this case, we are using tunneling as IP version 4 routers forwarding IP version 6 packets. So in this case, IP version 6 datagram will be embedded to an IP version 4 packet. Okay, so IP version 4 headers will be there, and then as a payload of IP version 4, there will be IP version 6 datagram itself. So when it reaches to the final destination, it will get only the IP version 6 datagram. Okay, so this is the idea. Now this is an example, tunneling and encapsulation, two IP6 routers. See, now connects to IP6 routers, no problem. It will carry IP6 datagram, or it can carry IP4 datagram. So doesn't matter actually. In data link layer frame, it incorporates the packet given by the network layer. So it can be IP version 6, it can be IP version 4, no problem. Okay, but what happens when there is a IP version 4 network connecting to IP6 routers? That means A and F completely IP version 6, they cannot work with IP version 4. So in this case, what we must have? We must have B and E, because in the intermediate IP version 4 network, there are all IP version 4 routers. So we must have dual stack router B and E to create that tunnel. Is the concept clear? So effectively, this is a tunnel that is created by B and E. So A and F will get only IP version 6, and intermediate routers in IP version 4 network will get all IP version 4. Only B and E will work as a translator here, creating the tunnel. How? Effectively, that is like this. IP version 4 tunnel connecting IP version 6 routers. So in the one end of the tunnel, it will receive an IPv6 packet, it will convert to version 4. In the other end, like in router E, it will receive an IPv4, it will convert to IPv6. Okay, like this. This is the logical view. It's a tunnel, like a tunnel. But if you physical view, you can see the C and D is completely IPv4. They will know nothing about IPv6. So when they get a packet of IPv4, they will just forward, no problem. But in that IPv4 packet, actually IPv6 packet is embedded. If you see a logical, then you can see, okay, from B to E, it's a IPv4 tunnel. So if I put a packet of IPv4 in B, that will be carried to IPv4 in E, and then E will convert to IPv6. So this is a more in-depth example. I think I will not go that much details, but if you go through the example, I think the concept is, I think, already clear. Anybody has any question? I think the concept, at least the concept is clear, but how you can implement is out of the scope of this course. Any question? And how much IPv6 is already adopted? In Google, it's Google's report. It says 30% of clients access services via IPv6. So it's still 30%, 70% via IPv4. National Institute of Standards and Technology, NIST, they have published a report. They normally publish reports on the technology. 1/3 of all US government domains are IPv6 capable. Okay, so 1/3 already, but it's still 2/3 not capable. And in other countries like our country and some areas, I think the percentage of adoption is very less still. Okay, so that's the part I wanted to deliver to you, the basic concepts of IPv6. That is also from chapter 4.
This part is also included in the series, sir?
Yes. This part is also. Actually, this is part of section 4.3. Okay, but previously I just skipped because I was not sure about the time. So now I think, okay, I should give you a basic concept about IPv6. It's simply a basic concept. It's nothing complex. If you go through that section from the textbook, I think you will understand the things better. Okay.
Sir, এটা কি সিটিতে ইনক্লুড থাকবে?
No. It will not be included in class test, but it will be included in final. Okay. The class test, today's lecture will not be included in the class test. Okay. So now let us start the last chapter of the syllabus, that is chapter 6. So in this slide, I have specified more precisely the subsections. You can see there are two subsections possibly, 6.1.1 and 6.1.2, but we will cover 6.1.1 only. Similarly, that is basic concepts about data link layer. Then 6.3, I think we will cover most of the things. In 6.4, we will cover 6.4.1 and then 6.4.3. Okay. Now, data link layer. What are the goals? So we have covered application layer, transport layer, and application transport both actually inside an end system. Both covered in end system. Okay, then we have covered network layer. Then in network layer we said no, not only end system, intermediate devices like routers, they also part of the network layer mechanism. So if there are 10 routers in the middle must be traveled, then all the routers must actually process the packets. Now we are in data link layer. So do you remember we said some layers are in software, some are in hardware? So which layers work in software again? Completely in software. Which layers?
Application, presentation, and
Application, presentation, and network. Right, Mohib, very good. Application, presentation, and network. So network layer is also implemented fully in software. Keep in mind. And ultimately, everything we transfer from our machines ultimately converted to signals. If you want to convert to signals, you must have the hardware, right? So up to network layer, you have no concept, or the machine has no concept of what are the hardware type, link type, or the signal type. Okay. Then which layer completely implemented in hardware? Completely. I said completely.
physical and link.
Actually, physical layer is completely part of the hardware. Data link is part of the hardware and software. Data link is the only layer that works because there must be an interface, right? There must be an interface. There must be an interface between software and hardware. So data link is the works as the interface between software and hardware. So it is hardware works with the physical layer, and the software works as the with the upper layers, right? Network, transport, and application. So that is one big thing in this chapter we have to think when we I think get the concepts in data link layer. Okay, now what are the principles behind the data link layer services? We have to understand that. First thing, error detection and correction. I think in chapter 1 during layering, I have also specified data link layer is the only layer that can correct errors. Why? Anybody? What is the logic behind that? Detection of error is done by every layer, but correction of the error is done only by the data link layer. Why? Because data link is the only layer that works at the bit level. If you want to correct errors, you must work at the bit level, right? The bit or bits, those are in error. If you can identify, then it's easier to correct, because if it is 0 in error, you have to make it 1. If it is 1 and in error, you have to make it 0. Simple. So data link layer is the only layer that can correct errors also. Then data link layer also shares a broadcast channel, multiple access, right? We use switch or hub to connect multiple devices. That means it is also the responsibility of data link layer how it can give access. Link layer addressing, MAC address. I think we have already specified some of the examples using MAC address in chapter 1. So here we will know how those MAC addresses are used by the data link layer. And then the LAN, local area network. The mostly used wired LAN protocol is Ethernet. We will cover a little bit of Ethernet, and then there is a concept called virtual LAN, where data link layer can be used to create grouping among the subnets or among the networks. But we will not cover virtual LAN. We will not have probably time to cover virtual LAN. Again, this type of concepts are covered in the professional course in CCNA. Also, some of the things we cover in theory, for example, the hands-on calculation of routing tables and other things, those you will not get in those professional courses. Anyway, so let us now, and then instantiation and implementation of various link layer technology in the internet. These are the goals of this chapter. But we will cover, due to the time limitation, we'll cover mainly the introduction part, then multiple access protocols, and then in the local area networks part, we will cover the MAC addressing, physical addressing. A very important protocol in data link layer is ARP, address resolution protocol, we will cover. And then we'll cover how switches creates their forwarding table, because you know difference between switch and hub you have done in the lab, I think. In hub, whoever sends a signal, it is sent to every node, but in switch it only sends to the destination. How? Because switch uses a database of MAC address information, so that it knows which port the destination is connected to. So you'll see how switch creates that MAC table. And then finally we will cover an example, a day in the life of a web request. So this example is actually a complete example, all the protocols, all the things we have covered in this class, so that this example will give you a complete scenario to know, to review the concepts what we have learned already. So this is the outline what we will cover in data link layer. Let us start about the data link layer concepts. The same diagram we have used start of the chapter in every new chapter. So the same thing here, but what I said when we discussed about application transport, there was no application transport layer in the middle in the router. And then when we started network layer, we said, okay, every router or the routers that are traversed will participate. But again, we said even router, even packet, it has a source IP and it is destination IP. So between the links, that source and destination IP normally will not change. That is an exception. Normally will not change. But there can be many links, right? Now, to transfer, the path calculation will be done by the network layer, but to transfer a packet from one node to the very next node using a very next node through a link, network layer is dependent on data link layer. So when we come to data link layer, now we will see the scope will be not end system to end system, not host to host. It will be only a single physical link. So that is a big concept that we need to think. So you can see the red colored links. So if you send data from this end system to another, for example, you're connecting to a server in the data center, you can see there are many links marked red, and each link actually follows one data link layer protocol. And this type of links can be wired or wireless. Okay, and we all know that the data link layer packet we call a frame that encapsulates a packet or datagram from the network layer. So what is the responsibility of link layer? Link layer has the responsibility of transferring datagram from one node to physically adjacent node over a link. Simply, when network layer gives a packet to data link layer, it will take the packet, it will encapsulate in a frame, and then it will convert to signals, and then just place the signals in the physical link. Then the signals will go to the next node, immediate next node. We don't know who is the final destination, but signals will go to the next node, and next node will receive the signals, convert to bits, bits to convert to frames, and then the data link layer will take the frame and remove the header. It will be the packet or datagram. It will be given to the upper layer. So that is the idea of data link. Any question, anybody? You can ask questions anytime. Okay. So I think the first section, actually, we have mentioned the concepts in chapter 1 when we covered the layering concept. So you can just match with those concepts. Okay. Again, there is a real life example. I think I have given this example during the routing algorithm also. When we say, okay, we are moving from, we are going from Dhaka to Chittagong, right? So you are planning to go from an address in Dhaka to an address in Chittagong. Then what you will do? You will plan, right? So what is the plan? Part of the plan will be the expense, distance, time. So all those things will be in your mind. Then you have to think, okay, I can go through bus, or I can go through train, or I can go through plane, right? But then if you go to bus, you have to go to the bus station from your home on the particular day. And then from the bus station, if you board on the bus will take you using different routes. Bus will take you to the Chittagong bus station. Then from the Chittagong bus station, you have to go to the particular place. So how many links we can think about here? Just approximately, how many links? From my home at Dhaka to an office or a home at Chittagong. How many links in the example? Anybody?
4.
Muhib, how many?
4.
4. Actually, if I just grossly categorize this, from my home to Dhaka bus station is 1 link. From Dhaka bus station to Chittagong bus station, although there can be variation, bus can go through different links, but we can think another link. And from Chittagong bus station to the Chittagong destination, 3rd link. So 3 links, right? Is it clear? If we consider these 3
Yes,
links,
sir.
when you start from your home on the day of the traveling, what are the possible options for transport? You cannot get bus direct away, right? So what are the possible options? You can take a rickshaw if it is nearby. You can take a CNG, you can take Uber, you can have your own private car. But for example, you have called Uber, what will be the address you will give? The Chittagong address or the Dhaka bus station?
Sir, Dhaka bus station.
Right, Dhaka bus station. Simple logic. So see, this Dhaka bus station is like your MAC address, data link address. But your final destination is Chittagong. So that is IP address. So if we think about 3 links, from home, you will call Uber with the address of Dhaka bus station. So not the final address. That is 1 link. So that is Uber is now 1 data link layer protocol. Or if you call a CNG, that is data link layer protocol. You call rickshaw, again you will give the address of Dhaka bus station, not the Chittagong final address. So that is data link layer. Now you go to the bus station, Dhaka bus station, you board on the bus. Bus will carry you to the Chittagong bus station, right? So bus is now your 2nd data link layer protocol. Link of what? Link of Dhaka bus station to Chittagong bus station. Is still the destination is not your final destination, right? Destination is Chittagong bus station. So this is about the data link layer. When you just reach the Chittagong bus station, then you will again maybe only available transport there is, for example, rickshaw. No other transport, for example. Then rickshaw is the data link layer protocol for that final link. Is it clear now? So if I say from Dhaka home to the Chittagong destination, that is network layer. But if you think every intermediate link, that is, there is a data link layer in the middle. Okay, so similar example here, but this example is from the textbook, Cities in America. So limousine is a car, from Princeton to JFK, John F. Kennedy airport, then JFK to Geneva. Geneva is a city in Europe, and then using train from Geneva to Lausanne. So that is the example. Use different data link layer. In this case, tourist who is traveling is the datagram or packet, and then transport segment is the communication link, and then transport mode is the link layer protocol, and travel agent is the routing algorithm that actually fixes the traveling. So is it clear? The real life example. Now datagrams or packets transferred by different link protocols over the different links. It can be Wi-Fi, wireless, it can be cellular, it can be wired link. One link can be Wi-Fi, one link can be Ethernet, right? normally when we take internet connection, right? They give the wired connection, optical fiber or UTP. They give the connection to my router, right? Wireless router. Then I create a Wi-Fi inside my home. So if I use a laptop using Wi-Fi, actually you can think about the link from ISP to my wireless router is wired, and then from a wireless router to my laptop is Wi-Fi wireless, right? So this is the case, and each data link layer protocol different services. That means what? That means, again, we have mentioned this in chapter 1. Transport layer and data link layer can provide reliability, but the data link layer reliability is not mandatory. So some of the links may provide reliability, some of the link protocols may not provide reliability. So that is the case. But if we use a data link layer protocol, particular protocol, then we can say, okay, this will provide reliability or not. Now, what are the services that data link layer provides? We have the basic concept. Now we have to know there are different type of services data link layer provides. First one is framing or link access. Framing means it will take a datagram or packet from network layer. It will add header and trailer, so it will call the frame. So framing, at the source it will do that. At the receiving end, it will remove the headers, so the packet or datagram will be handed over to network layer. That is called framing. Second one, link access, wired link, wireless link, Wi-Fi, right? Cellular. So there are different type of links. Data link layer is the responsible layer that will actually fix how different devices will be given access to the link. MAC address is one of the mechanism, so that all the devices will know each other's MAC, or when a frame is received, it will know whether or not that frame is for its own purpose. So if not, it will discard the frame. If it is for this machine, then it will hand over the packet to the upper layer. Okay, so this is the framing and link access. Second thing is reliable. Already we have said data link layer can provide reliability. Even if it provides reliability, it will be only between adjacent nodes. Adjacent nodes means only within a link. Transport layer gives reliability from source to destination, but data link layer can provide reliability only in a link. Very next link may not have the reliability. So that is the case. Now there is a question, why both link level and end-to-end reliability we need? Okay, I am asking this to you. Anybody has an answer? We said transport layer gives the reliability, that is end-to-end. Now we are saying data link layer also gives reliability. So why we need both link level and end level reliability? If transport layer can give reliability, why we need data link layer reliability? Any idea? Can you share with me? Kalam, can you tell me? Pratik? Rakibul? Just we can participate. Why we need both type of reliability? What is the advantage? Okay, if link layer gives the reliability, what is the advantage? If a link gives the reliability, do we need to transfer that frame or that packet from the transport layer? Yes or no?
Yes, sir.
For example, what I said, suppose a frame is lost in a particular link, and data link layer gives reliability. That means data link layer will retransmit, right? In that case, do we need still transport layer to retransmit that packet? No, because if data link layer retransmits the frame, that means the frame is already retransmitted, so transport layer is not needed in this case. But the problem is not all the layers are giving reliability. So that means if we remove the reliability from transport layer, then some other links might drop packet and they will not retransmit. But if a particular data link layer gives reliability, then it will be definitely faster, right? It will be definitely faster because the previous node will retransmit again instead of the source end system. You got my point? Is it clear? So that's why we need both link level and end-to-end reliability. Okay. Now the third one, flow control. I think we have already mentioned this during the layering concept. Both transport layer and data link layer gives flow control, but the data link layer flow control is actually between again adjacent nodes in terms of bit rate. Suppose one machine has 10 Mbps LAN card, right? 10 megabits per second. Another machine is connected with that with 100 megabits per second. Is it compatible directly? One has 10 speed, one has 100 speed. How they will communicate? What can we do in this case? Should we transmit at 100 Mbps or do we transmit 10 Mbps? What is logical? Tell me.
10.
Right, because in 100 Mbps, that's not possible for the other node with 10 Mbps to receive, right? So 10. Okay, now data link layer has this responsibility. If there are multiple nodes, I think in the network lab, probably you have noticed some of the switch ports has 1 Gbps speed, right? And some other ports has 100 Mbps speed, right? Did you notice that? Even
Yes, sir.
even if you buy a simple 500 600 taka switch or hub from the market, you will get in the specification over the packet, you will get the specification 10/100 Mbps connection. That means if your machine supports 10 or if your machine support 100, you can connect all those machines using the same hub, same switch. Then how it will work? Because the switch in data link layer, it can actually control that flow between 10 and 100 Mbps devices. So that is the flow control. And as we said, it must be the lowest one. Okay, error detection. Already we have mentioned several times. Error detection, error caused by signal attenuation, noise, or physical some other errors. It whenever a packet is received by a node, its data link layer will check errors. If there is an error, then it will be discarded. And then error correction. Receiver identifies and corrects bit errors without retransmission. Okay, so error correction, if it can be done by the node, it's much better, but again error correction is not always possible, so that's why we need retransmission if there are some errors. And finally, half duplex and full duplex. So if the connection is half duplex, like hub is half duplex, that means at one time one can communicate. For example, walkie-talkie, right? Half duplex. And full duplex means both way communication can be done. So switch has the property, data link has the property of setting as half duplex or setting as full duplex. No problem. So these are the services provided by data link layer. Any question? Anybody? And where is the link layer implemented? We all know there is a LAN card, network interface card. So if we that is built in laptops and some other motherboards, or you can buy a LAN card and you can put this in your motherboard. But whatever you do, there are two parts in the data link layer. I have already mentioned. One part is the hardware controller part. Another part is the software that works with the CPU. So data link layer you can convert into two different parts. Okay, so let us stop here today, although we have some time left, but I want to start this topic on next class. So by that time, let us discuss if you have any further problems in this lecture or in any other lecture. Any problem? Okay, so this section actually, yes,
Quiz will be on chapter 4 and chapter 5, right?
right. 4.1, 4.3, and 5.2. We have read only 3 sections in 4 and 5. Okay.
This today's lectures will not be included.
No, it will not be included. Right.
Okay, sir. Thank you, sir.
Okay, so this section on multiple access links and protocols will start on next class, and then we'll have 2 more classes. So hopefully we can have the second part of the class for discussion before the final exam. Okay, so anybody has any question on any part? And as I have already requested you to start the homework as early as possible. Hopefully everyone started. Those who not started yet, I think you will find some difficulty, but please do it as early as possible. And the syllabus of class test is actually mostly the syllabus of homework. And also I have uploaded the study guide. This is, I think, updated for version 7 of the textbook, so you can also follow this as the guideline what we have covered. So we have only covered 6.1 today, and we have to cover 6.3 and then 6.4. Okay, no question from your side? Then let me take the attendance. Please respond. Okay, Raihan Chaudhuri, Himel Mojumdar, Shahin Alam.
Yes, sir.
Okay, Shahin present. Tarek Mahmood,
Present, sir.
Arafat Rahman, Tasneem Faria.
Present, sir.
Sir, Arafat Rahman Ashi, sir.
Okay, Arafat present. Khushnur.
Sir.
Okay, Shajib,
Yes, sir.
Mohimul Badr present. Tauhidur Rahman.
Yes, sir. Mohimul.
Yes. Karishma Haq,
Present, sir.
Mohammad Abdullah,
Yes, sir.
Shahriyar Jaman,
Yes, sir.
Mahbub Rahman, Khondokar Mahmudur Rahman, Noor Hussain.
Yes, sir.
Okay, Mahmud present. Okay. Noor Hussain.
Yes, sir.
Mahmud, are you there? Khondokar Mahmudur Rahman.
Yes, sir.
Okay, Noor present. Okay. Sayyada Tahsina,
Yes, sir.
Sumaya Haq,
Present, sir.
Muntaha, Sayyada Muntaha,
Present, sir.
Rajia.
Yes,
Muntaha, are
sir.
you there?
Yes, sir.
Okay, Razia present.
Sir,
Mahmudul Hassan.
Khondokar Mahmudur Rahman is present, sir.
Yeah, yes, present. Khondokar Mahmud present. Okay, Mahmudul Hassan, Abdullah Al Fahad.
Yes, sir.
Okay, Pratik present. Sabbir Hussain,
Present, sir.
Farhana Akhtar,
Present, sir.
Manik Hussain. Okay, Farhana present. Manik Hussain. Manik, are you there?
Yes, sir.
Okay, Saleh Akram, Ahmad Musa,
Yes, sir.
Hassan Shaun,
Yes, sir.
Mainul Karim.
Yes, sir.
Okay, Muhib present. Nazma Akhtar, Millat Hussain.
স্যার নাজমা আক্তার স্যার
Present,
ছিল
sir.
স্যার এটা।
Okay.
Millat
Okay,
Hussain.
Nazma. Okay, Millat present. Ahmed Raihan, Jahidul Islam,
Yes, sir.
Shah Poran,
Yes, sir.
Tahalil Azim,
Present, sir.
Anisur Rahman. Anis, are you there? Mohammad
Yes, sir.
Tanvir.
I'm present.
Okay,
Present,
Anis
sir.
present. Okay, Tanvir
Sir,
present.
Tanvir.
Okay, Ridwanur Rahman,
Yes, sir.
Imran Hussain.
Sir, Imran
Imran.
Hossain Shilo, sir.
Okay, Mirja.
Yes, sir.
Anand. Anand, are you there? Ashikul Islam.
Yes, sir.
Yusuf Ali.
The chat box লিখছে।
Okay, Abu Kalam present. Shojol present. Rakib present. Okay, anyone else?
Sir, Nur Hossain.
Nur Hussain present. Anyone else?
Sir,
Okay.
Mahimul Bodor, sir.
Bodor present.
Okay, sir.
Sir,
Okay, তাহলে খন্দকার মোহাম্মদ মাহমুদুল হাসান আর খন্দকার মাহমুদুল হাসান। খন্দকার মাহমুদুর রহমান। Mohammad Mahmudul Hassan. Okay, present. Anyone else? Okay, then thank you very much. Let us end class today. See you in the next class. Next class we will have our class test 5. Okay. Okay. Stop recording.